The Great Pyramid of Giza stands 146.7 meters tall. When you multiply this height by 43,200, you get to 199,792,458, the exact speed of light in meters per second. This isn't an approximation. This isn't a coincidence. This is mathematical precision that challenges everything we think we know about ancient Egyptian capabilities and the true purpose of history's most enigmatic monument. For over 4,500 years, the Great Pyramid has guarded its secrets on the Giza Plateau. But recent mathematical analysis has revealed encoded information that suggests the ancient builders possessed scientific knowledge far beyond what conventional archaeology acknowledges. The pyramid's dimensions, when subjected to specific mathematical operations, yield fundamental physical constants with accuracy that modern science achieved only in the past century. The speed of light wasn't officially measured until 1676, when Ulrimer used Jupiter's moons to make the first reasonable calculation. Albert Michelson's precise interferometry experiments in the 1920s established the value we use today, 299,792,458 meters per second. Yet mathematical analysis of pyramid dimensions suggests this exact value was encoded in stone over for millennia before European science discovered it. Tonight we're investigating one of the most extraordinary claims in alternative archaeology, that the Great Pyramid functions as a massive repository of encoded scientific knowledge, with the speed of light representing just one of multiple fundamental constants hidden within its geometric structure. We'll examine the mathematical evidence, explore how ancient builders might have possessed such knowledge, and investigate whether these correlations represent intentional encoding or remarkable coincidence. The mathematical relationships extend far beyond simple height measurements. The pyramid's base perimeter, when divided by its height, yields pi to several decimal places. The ratio of the pyramid's base to its height equals the golden ratio phi. The angle of the pyramid's sides, 51.84 degrees, creates geometric relationships that encode multiple fundamental constants simultaneously. Dr. Scott Creighton, an engineer and pyramid researcher, has spent decades analyzing the geometric properties of Egyptian monuments. His mathematical analysis reveals that pyramid builders employed sophisticated understanding of advanced mathematics, including trigonometric relationships, irrational numbers, and geometric principles that wouldn't be formally developed in European mathematics for thousands of years. The precision required for these mathematical relationships demands construction accuracy that challenges conventional understanding of ancient capabilities. The Great Pyramid's base square measures to 130.4 meters per side with less than 2 centimeters variation precision that modern construction struggles to achieve. The orientation aligns with true north to within 3/60th of a degree, demonstrating surveying capabilities that suggest advanced knowledge of Earth's rotational and orbital mechanics. Archaeological evidence supports the possibility of sophisticated ancient knowledge through artifacts that demonstrate advanced metallurgy, precision machining, and mathematical understanding. The Antikythera mechanism, discovered in a Greek shipwreck, reveals mechanical computing capabilities from the 1st century BC that weren't redeveloped until the Renaissance. Similar technological sophistication might have enabled the mathematical encoding claim for the pyramids. The Egyptian mathematical papyri, including the Rhind papyrus and Moscow papyrus, document advanced mathematical techniques including accurate approximations of pi, complex geometric calculations, and algebraic methods. These texts demonstrate that ancient Egyptian mathematicians possessed far more sophisticated understanding than typically acknowledged in conventional archaeological interpretations. Recent ground-penetrating radar and cosmic ray-wound tomography have revealed previously unknown chambers and structural features within the Great Pyramid. These discoveries suggest that pyramid architecture includes levels of complexity not visible through external observation, potentially supporting theories that the structure encodes multiple layers of mathematical and scientific information. The historical context adds intrigue to these mathematical discoveries. Ancient Egyptian civilization achieved remarkable feats in engineering, astronomy, and mathematics that required advanced scientific understanding. the precision of pyramid construction, the accuracy of astronomical alignments, and the sophisticated mathematical relationships embedded in temple architecture suggest capabilities that exceed convent archaeological estimates. Cross-cultural evidence reveals similar mathematical encoding in ancient structures worldwide. Stonehenge demonstrates astronomical alignments that encode Earth's orbital mechanics. Angkor Wat incorporates cosmological constants into its architectural proportions. The Mayan pyramids embody mathematical relationships that reflect advanced understanding of planetary cycles and calendrical calculations. The implications challenge fundamental assumptions about the development of human knowledge. Ancient builders intentionally encoded the speed of light into pyramid dimensions. It suggests access to scientific information through means not recognized by conventional academic archaeology. This possibility forces reconsideration of linear progress models that assume scientific knowledge develops continuously from primitive to sophisticated. Modern digital analysis enables unprecedented precision in measuring and analyzing ancient structures. Laser scanning technology can detect dimensional variations measured in millimeters across structures spanning hundreds of meters. Computer analysis can identify mathematical patterns that might escape manual measurement and calculation, revealing relationships that previous researchers couldn't detect. The mathematical encoding hypothesis generates testable predictions that can be verified through rigorous measurement and analysis. If pyramids intentionally encode scientific constants, similar mathematical relationships should appear consistently across multiple structures, demonstrating systematic knowledge rather than coincidental correlation. Peer-reviewed research by mathematicians and engineers increasingly supports claims of sophisticated, ancient mathematical knowledge. Papers published in journals like the Journal of Ancient History and Archaeology document mathematical relationships in ancient architecture that demonstrate precision and complexity, exceeding conventional estimates of ancient capabilities. The technological requirements for achieving the mathematical precision claimed in pyramid encoding suggest advanced capabilities in surveying, mathematics, and construction that challenge conventional timelines for human technological development. Understanding how ancient builders achieved such precision could inform modern engineering and construction techniques. If you're intrigued by evidence that challenges conventional archaeological assumptions, subscribe and hit that thumbs up button. Here is a question that frames our entire investigation: if ancient builders could encode the speed of light with mathematical precision, what other scientific knowledge might be hidden in plain sight within ancient structures? The journey ahead examines mathematical evidence, explores historical possibilities, and investigates the scientific implications of encoded knowledge in ancient architecture. From precise measurements of pyramid dimensions to analysis of construction techniques, from mathematical relationships to historical context, we are exploring whether the Great Pyramid genuinely encodes the speed of light and what this might reveal about the true capabilities of ancient human civilization. Now let's begin by examining the specific mathematical relationships that connect pyramid dimensions to fundamental physical constants. Sacred geometry. The Great Pyramid's geometric relationships reveal mathematical principles that encode fundamental physical constants with precision that challenges conventional understanding of ancient mathematical capabilities. These relationships extend far beyond simple dimensional correlations to encompass complex geometric theorems, trigonometric functions, and mathematical constants that demonstrate sophisticated knowledge of advanced mathematics and physics. The primary mathematical relationship connecting the pyramid to the speed of light emerges from the precise measurement of its original height multiplied by a specific scaling factor. The Great Pyramid's original height, including its missing capstone, measured 146.7 meters. When multiplied by 43,200, a number that appears frequently in ancient cosmological calculations, the result equals 299,792,400, which approximates the speed of light in meters per second to within 0.02% accuracy. The scaling factor 43,200 itself encodes astronomical knowledge, representing exactly half the number of years in Earth's full precession cycle. Ancient astronomical texts from various cultures reference this 86,400-year cycle, suggesting widespread knowledge of long-term celestial mechanics that requires sophisticated observational capabilities sustained across millennia. Base perimeter calculations reveal additional mathematical encoding beyond the speed of light relationship. The golden ratio phi 1.61803 appears throughout pyramid geometry in relationships that demonstrate sophisticated understanding of irrational numbers and their geometric properties. The ratio of the slant height to half the base length equals phi, while the ratio of the pyramid's height to its base apothem also yields phi. These relationships require advanced mathematical understanding and precise construction to achieve. Trigonometric relationships embedded in pyramid geometry reveal knowledge of complex mathematical functions. The pyramid's slope angle of 51.84 degrees creates a triangle where the ratio of height to base radius equals 4 pi, encoding pi within the pyramid's fundamental geometric proportions. This relationship connects multiple mathematical constants within a single architectural element. Volume and surface area calculations yield additional mathematical constants when subjected to specific operations. The pyramid's volume of 2,583,283 cubic meters, when divided by its surface area of 85,500 square meters, produces ratios that approximate fundamental mathematical constants including Euler's number and various trigonometric values. The precision required to achieve these mathematical relationships demands construction accuracy that exceeds typical ancient building tolerances. Modern laser measurement reveals that pyramid base dimensions vary by less than 2 centimeters across 230-meter spans, precision that requires advanced surveying techniques and sophisticated understanding of geometric principles. Coordinate system encoding appears in the pyramid's geographic positioning, where its latitude and longitude coordinates relate to fundamental constants through specific mathematical operations. The pyramid's latitude of 29.979 to 458 degrees north approximates the first 9 digits of the speed of light when interpreted numerically, suggesting intentional geographic placement based on mathematical considerations. Internal chamber proportions continue the pattern of mathematical encoding found in external dimensions. The King's chamber dimensions create geometric relationships that yield mathematical constants including pi, phi, and various square roots of small integers. The chamber's granite construction enables precise dimensional control necessary for maintaining these mathematical relationships. Numerical analysis of construction unit measurements reveals systematic encoding of mathematical constants throughout pyramid architecture. The royal cubit measurement system employed in pyramid construction creates ratios that approximate fundamental constants when applied to overall structural dimensions, suggesting integration of mathematical encoding within the measurement standards themselves. Geometric theorem applications demonstrate advanced mathematical knowledge through relationships that wouldn't be formally proven until centuries later. The pyramid embodies principles of solid geometry, including relationships between circumscribed and inscribed figures that anticipate mathematical discoveries attributed to later Greek geometers. Astronomical alignment encoding connects mathematical constants to celestial mechanics through precise orientation and angular relationships. The pyramid's cardinal alignment accuracy of 3/60th degree requires understanding of Earth's rotation and stellar movement that enables detection of true north with extraordinary precision. Proportional analysis reveals mathematical relationships that extend beyond coincidental correlation to demonstrate systematic knowledge of advanced mathematics. The consistency of mathematical encoding across multiple dimensional relationships suggests intentional design rather than accidental approximation of fundamental constants. Sacred proportion systems from ancient mathematical traditions provide context for understanding how mathematical constants could have been integrated into architectural design. Egyptian mathematical papyri document sophisticated calculation methods that could support the complex mathematical operations required for encoding fundamental constants. Construction technique analysis reveals engineering methods that could achieve the precision necessary for mathematical encoding. Advanced stone cutting tools, sophisticated lifting equipment, and precise surveying instruments enable accuracy levels that support intentional mathematical relationships rather than approximation. Cross-structure comparison shows similar mathematical encoding in other ancient Egyptian monuments. Suggesting systematic knowledge rather than isolated achievement, the smaller pyramids at Giza demonstrate proportional relationships that echo the mathematical patterns found in the Great Pyramid, indicating widespread application of advanced mathematical principles. Measurement system integration reveals how ancient units of measurement could encode mathematical constants through systematic relationships. The royal cubit, when applied to pyramid dimensions, creates ratios that approximate fundamental constants through relationships that suggest intentional design rather than coincidental correlation. Quality control mechanisms in pyramid construction demonstrate capabilities for achieving and maintaining mathematical precision across large-scale construction projects. The consistency of mathematical relationships throughout pyramid architecture requires construction oversight that can detect and correct deviations from target mathematical values. Archaeological evidence for advanced mathematical knowledge includes artifacts that demonstrate computational capabilities and geometric understanding that could support the mathematical sophistication claimed for pyramid encoding. Ancient Egyptian mathematical tools, calculation methods, and geometric instruments provide context for the advanced mathematics evident in pyramid architecture. Modern verification techniques enable unprecedented precision in measuring and analyzing pyramid mathematical relationships. Laser scanning, photogrammetry, and computer analysis can detect mathematical patterns with accuracy that previous generations of researchers couldn't achieve, revealing relationships that manual measurement might miss. Statistical analysis of mathematical relationships in pyramid geometry can distinguish between intentional encoding and coincidental correlation. The frequency, precision, and consistency of mathematical constants in pyramid proportions exceed probability thresholds for random occurrence. Supporting theories of intentional mathematical encoding, theoretical frameworks from mathematics and physics provide context for understanding how fundamental constants could have been discovered and encoded by ancient builders. Mathematical relationships between physical constants suggest natural pathways for discovering speed of light values through geometric and astronomical investigations. The geometric foundations of pyramid architecture thus demonstrate mathematical sophistication that encompasses fundamental constants, advanced geometric relationships, and engineering precision that challenges conventional assessments of ancient mathematical capabilities. These relationships suggest systematic knowledge of advanced mathematics that enabled intentional encoding of scientific information within architectural proportions. Measuring light. The historical development of light speed measurement reveals the extraordinary scientific achievement required to determine this fundamental constant, making its alleged encoding in pyramid architecture all the more remarkable. Understanding how modern science determined the speed of light provides crucial context for evaluating whether ancient builders could have possessed this knowledge through alternative means or methodologies. Galileo Galilei made the first systematic attempt to measure light speed around 1638 using lanterns and human reaction time, but his methods proved inadequate for detecting light's enormous velocity. His experiments demonstrated that light traveled much faster than sound but couldn't determine specific values, establishing that light speed measurement required more sophisticated techniques than 17th century technology could provide. Alzheimer achieved the first reasonable light speed calculation in 1676 through astronomical observations of Jupiter's moon Io. By measuring timing variations in lunar eclipses as Earth's orbital position changed relative to Jupiter, Reimer calculated light speed at approximately 214,000 kilometers per second, about 30% lower than the actual value, but demonstrating the correct order of magnitude. James Bradley refined light speed estimates in 1728 through stellar aberration observations, measuring how star positions appeared to change as Earth moved through its orbit. Bradley's method yielded light speed values closer to 300,000 kilometers per second, representing significant improvement over Reimer's calculations while demonstrating astronomical approaches to measure In fundamental physical constants, Hippolyte Fizeau conducted the first terrestrial light speed measurement in 1849 using a rotating toothed wheel apparatus that interrupted light beams across measured distances. Fizeau's ingenious mechanical method achieved light speed measurements of 315,000 kilometers per second, proving that precise light speed determination was possible using ground-based experiments rather than requiring astronomical observations. Leon Foucault improved Fizeau's approach in 1862 using rotating mirrors instead of toothed wheels, achieving greater precision and measuring light speed at 298,000 kilometers per second. Foucault's mirror method demonstrated that increasingly sophisticated instrumentation could approach true light speed values with remarkable accuracy for 19th century technology. Albert Michelson revolutionized light speed measurement through interferometry techniques developed during the 1920s, achieving unprecedented precision using interference patterns created by splitting and recombining light beams. Michelson's methods measured light speed at 299,792,458 meters per second, the value still used today and allegedly encoded in pyramid dimensions. The extraordinary precision achieved by Michelson's interferometry required sophisticated understanding of wave optics, mechanical engineering, and statistical analysis that represents the culmination of centuries of scientific development. The technology and mathematical techniques necessary for precise light speed measurements seemed far beyond ancient capabilities, making claimed pyramid encoding all the more intriguing. Theoretical frameworks for understanding light speed emerged gradually through electromagnetic theory developed by James Clerk Maxwell in the 1860s. Maxwell's equations predicted that electromagnetic radiation, including light, travels at specific velocities determined by fundamental properties of space and time. This theoretical foundation enabled scientists to understand why light speed represents a universal constant rather than variable velocity. Modern quantum electrodynamics provides additional context for understanding light speed as a fundamental feature of spacetime geometry, rather than simply a property of electromagnetic radiation. The speed of light represents the maximum velocity at which information can propagate through space, connecting light speed to fundamental aspects of physical reality that go beyond simple measurement of electromagnetic phenomena. Alternative measurement approaches demonstrate multiple pathways for determining light speed values, suggesting that ancient investigators might have discovered this constant through methods not recognized by conventional scientific history. Astronomical timing, geometric relationships, and mathematical modeling could theoretically enable light speed determination without modern technological requirements. Ancient astronomical capabilities evident in pyramid construction and alignment demonstrate sophisticated understanding of celestial mechanics that could theoretically support light speed investigation. The precision of pyramid astronomical orientations requires observational capabilities and mathematical modeling that might enable detection of light propagation delays across cosmic distances. Mathematical relationships between light speed and other fundamental constants suggest natural pathways for discovering electromagnetic constants through investigations of geometric relationships and physical proportions. The fine structure constant, for example, connects light speed to electron charge and quantum mechanics through mathematical relationships that might be discoverable through pure mathematics. Experimental archaeology techniques can evaluate whether ancient measurement tools and techniques could achieve the precision necessary for light speed determination. Reconstruction of ancient astronomical instruments using traditional materials and methods can demonstrate practical capabilities available to ancient investigators pursuing fundamental physical constants. Cross-cultural evidence for advanced ancient knowledge includes references to light propagation and electromagnetic phenomena in various historical traditions that might indicate systematic investigation of light properties. Sanskrit texts, Chinese astronomical records, and other ancient sources contain descriptions that might represent early investigations into electromagnetic phenomena. Technological archaeology reveals ancient capabilities that exceed conventional estimates of historical technological sophistication. The Antikythera mechanism demonstrates mechanical computing abilities that could theoretically support complex calculations required for fundamental constant determination through astronomical observation and mathematical modeling. Precision measurement capabilities in ancient architecture demonstrate accuracy levels that could support systematic investigation of fundamental physical relationships. The engineering precision evident in pyramid construction suggests measurement and calculation capabilities that might enable detection of electromagnetic constants through geometric and astronomical investigations. Information preservation mechanisms in ancient cultures could have maintained knowledge of fundamental constants across generations through encoding within architectural proportions, mathematical relationships, and systematic measurement standards. The integration of scientific knowledge within practical applications could ensure preservation even during periods of reduced scientific activity. Collaborative investigation scenarios suggest how ancient communities might have achieved light speed determination through coordinated observational programs extending across multiple locations and time periods. Systematic astronomical observation coordinated between distant sites could theoretically enable detection of light propagation delays that reveal electromagnetic constant values. Statistical analysis of claimed pyramid encoding can evaluate whether mathematical relationships between pyramid dimensions and light speed represent intentional knowledge or coincidental correlation. Probability calculations considering the precision of mathematical relationships and the number of potential correlations can assess the likelihood of accidental correspondence. Modern verification protocols enable systematic testing of claims about ancient scientific knowledge through rigorous measurement and analysis of architectural proportions. Laser measurement, computer modeling, and statistical analysis can identify mathematical patterns with precision that enables objective evaluation of encoding claims. Reverse engineering approaches can investigate how ancient builders might have achieved mathematical precision in encoding fundamental constants, evaluating construction techniques and design methodologies that could produce observed mathematical relationships. Understanding ancient capabilities provides context for assessing the plausibility of intentional constant encoding. Replication studies attempt to reproduce claimed mathematical relationships using ancient measurement systems and calculation methods, testing whether proposed encoding mechanisms could actually produce observed correlations. Experimental validation of encoding methodologies provides crucial evidence for evaluating ancient scientific capability claims. The measurement of light speed thus represents one of science's greatest achievements, requiring sophisticated methodology and extraordinary precision that seemingly exceeds ancient technological capabilities. Yet the alleged encoding of this constant in pyramid dimensions suggests the possibility of alternative discovery pathways that challenge conventional assumptions about the development of scientific knowledge throughout human history. Hidden mathematics. The mathematical relationships embedded within pyramid architecture extend far beyond single correlations to encompass multiple interconnected constants and geometric principles that suggest systematic encoding of advanced mathematical knowledge. These patterns demonstrate mathematical sophistication that challenges conventional estimates of ancient computational capabilities while revealing potential preservation mechanisms for scientific information. The Pythagorean theorem applications throughout pyramid geometry demonstrate advanced understanding of mathematical relationships centuries before Pythagoras formally described them. In Greek mathematics, the pyramid's triangular faces embody perfect right triangle relationships where the sum of squared sides equals the squared hypotenuse, requiring sophisticated understanding of geometric principles and precise construction capabilities. Trigonometric function encoding appears through specific angle relationships that yield exact values for sine, cosine, and tangent functions. Logarithmic relationships between pyramid dimensions reveal advanced mathematical understanding that anticipates mathematical concepts not formally developed until much later in mathematical history. The ratios between various pyramid measurements, when expressed logarithmically, yield values that approximate natural logarithm bases and other mathematical constants fundamental to advanced mathematics. Geometric series applications demonstrate sophisticated understanding of infinite series and convergence principles. The pyramid's diminishing step pyramid internal structure, revealed through recent scanning technology, embodies geometric progression principles where each level maintains specific proportional relationships to overall pyramid dimensions. Calculus anticipation appears through mathematical relationships that require understanding of limiting processes and infinitesimal analysis. The mathematical relationships between pyramid surface area, volume, and edge measurements involve concepts that anticipate differential and integral calculus development by centuries or millennia. Number theory applications throughout pyramid architecture demonstrate understanding of prime numbers, perfect numbers, and other mathematical concepts that represent advanced theoretical mathematics. The numerical relationships between pyramid measurements often involve prime factorizations and number sequences that suggest systematic mathematical knowledge. Complex number relationships appear through geometric constructions that require understanding of imaginary numbers and complex plane mathematics. Certain pyramid geometric relationships, when analyzed using complex mathematics, yield elegant solutions that suggest ancient builders understood mathematical concepts not formally developed until the Renaissance. Matrix mathematics applications emerged through structural relationships that can be expressed using linear algebra techniques. The three-dimensional geometry of pyramid construction creates mathematical relationships that can be analyzed using matrix operations, revealing systematic mathematical principles underlying architectural design. Fractal geometry principles appear in pyramid construction details and proportional relationships that demonstrate understanding of self-similar geometric patterns. The mathematical relationships between pyramid dimensions at different scales embody fractal properties that anticipate modern mathematical concepts by thousands of years. Statistical mathematics applications demonstrate understanding of probability, error analysis, and quality control principles necessary for achieving mathematical precision in large-scale construction. The consistency of mathematical relationships across pyramid architecture requires statistical understanding that enables systematic quality control during construction. Topology concepts appear through mathematical relationships that remain invariant under geometric transformations. The essential mathematical relationships encoded in pyramid geometry persist despite changes in measurement units or coordinate systems, demonstrating understanding of topological principles that represent advanced mathematical thinking. Group theory applications emerge through symmetry relationships and transformation properties embedded in pyramid architecture. The mathematical symmetries of pyramid construction embody group theory principles that demonstrate sophisticated understanding of mathematical structure and algebraic relationships. Optimization theory principles appear through architectural solutions that maximize specific mathematical relationships while satisfying multiple geometric constraints simultaneously. The pyramid design represents solutions to complex optimization problems that require advanced mathematical understanding and computational capabilities. Harmonic analysis applications demonstrate understanding of periodic phenomena and frequency relationships through geometric proportions that embody harmonic series and resonance principles. The mathematical relationships between pyramid dimensions create harmonic ratios that suggest understanding of wave mathematics and vibrational principles. Combinatorial mathematics appears through construction relationships that demonstrate understanding of permutation and combination principles. The arrangement of pyramid blocks and architectural elements embodies combinatorial optimization that suggests advanced mathematical planning and calculation capabilities. Game theory principles emerge through construction decisions that represent optimal solutions to resource allocation and construction scheduling problems. The pyramid construction process required mathematical optimization that anticipates game theory and decision analysis techniques. Information theory concepts appear through encoding mechanisms that demonstrate understanding of data compression, error correction, and information preservation principles. The mathematical relationships embedded in pyramid architecture represent sophisticated information encoding that anticipates modern information theory development. Chaos theory anticipation emerges through mathematical relationships that demonstrate sensitivity to initial conditions and nonlinear dynamics. Certain pyramid geometric relationships exhibit properties that suggest understanding of complex dynamical systems and chaotic behavior principles. Differential geometry applications appear through curved surface approximations and geometric relationships that anticipate mathematical concepts not formally developed until modern mathematics. The pyramid's geometric properties embody differential geometry principles that represent advanced mathematical understanding. Abstract algebra concepts emerge through mathematical relationships that demonstrate understanding of group structures, field properties, and algebraic operations. The systematic mathematical relationships throughout pyramid architecture embody abstract algebraic principles that anticipate modern mathematical development. Set theory principles appear through classification and organization systems that demonstrate understanding of mathematical structure and logical relationships. The systematic organization of mathematical relationships within pyramid architecture embodies set theory concepts that represent advanced mathematical thinking. Logic and proof theory applications demonstrate understanding of mathematical reasoning and formal proof techniques. The consistency and systematicity of mathematical relationships throughout pyramid architecture suggest understanding of logical principles and mathematical proof methodology. Real analysis concepts appear through mathematical relationships that demonstrate understanding of limits, continuity, and convergence principles. The mathematical precision achieved in pyramid construction requires understanding of real analysis concepts that anticipate modern mathematical development. Algebraic geometry applications emerge through relationships between geometric constructions and algebraic equations. The mathematical relationships embedded in pyramid geometry can be expressed through algebraic equations that demonstrate sophisticated understanding of mathematical structure. Mathematical physics applications appear through relationships that connect geometry to physical principles and natural constants, the encoding of fundamental physical constants within geometric relationships suggests understanding of mathematical physics principles that anticipate modern theoretical physics development. The mathematical sophistication demonstrated through pyramid architecture thus encompasses virtually all branches of advanced mathematics. From elementary geometry through modern theoretical mathematics, this comprehensive mathematical encoding suggests systematic preservation of advanced mathematical knowledge that challenges conventional timelines for mathematical development while revealing sophisticated ancient understanding of mathematical principles. Ancient engineers. The engineering capabilities demonstrated in Great Pyramid construction reveal technological sophistication that could theoretically support the precision required for encoding mathematical constants while challenging conventional assessments of ancient technological capabilities. Understanding these engineering achievements provides crucial context for evaluating whether intentional constant encoding represents feasible ancient accomplishment or impossible anachronism. Precision surveying techniques evident in pyramid construction demonstrate accuracy that approaches modern geodetic standards while utilizing technologies available in ancient Egypt. The pyramid's cardinal orientation accuracy of 3/60th degree requires surveying methods that can detect true north with extraordinary precision, suggesting advanced understanding of astronomical observation and mathematical calculation. The surveying methodology likely involved long-term stellar observations using techniques that track star positions across multiple observation periods to eliminate systematic errors. This approach requires understanding of precession, atmospheric refraction, and stellar motion that demonstrates sophisticated astronomical knowledge combined with mathematical error analysis capabilities. Foundation engineering for pyramid construction required precision that exceeds typical ancient building standards by orders of magnitude. The pyramid base deviates less than 2.1 centimeters from perfect square across 230-meter dimensions, achieving flatness accuracy that modern construction struggles to match using contemporary equipment and quality control methods. Achieving this foundation precision required advanced techniques for site preparation, elevation measurement, and quality control that suggests sophisticated engineering capabilities. The foundation work demonstrates understanding of principles including soil mechanics, structural loading, and geometric accuracy that enable precise construction across enormous scales. Stone cutting and shaping technologies achieve precision that enables tight joints between massive blocks while maintaining overall structural accuracy necessary for mathematical encoding. The granite blocks in internal chambers demonstrate machining accuracy that suggests advanced cutting tools and measurement techniques that exceed conventional estimates of ancient technological capabilities. The engineering precision required for mathematical constant encoding demands quality control mechanisms that can detect and correct deviations from target mathematical relationships. This level of precision control requires measurement technologies, calculation methods, and construction oversight that represent advanced engineering management capabilities. Lifting and positioning equipment for pyramid construction required mechanical engineering sophistication that enables precise placement of multi-ton blocks while maintaining overall structural accuracy. The construction process demonstrates understanding of mechanical advantage, structural stability, and precision placement that suggests advanced engineering knowledge and sophisticated equipment design. Material selection and quality control demonstrate understanding of structural engineering principles that ensure long-term stability while maintaining mathematical precision. The choice of limestone for structural elements and granite for precision components suggests engineering knowledge that optimizes material properties for specific construction requirements. Architectural design integration requires engineering capabilities that coordinate multiple structural systems while maintaining mathematical relationships across all architectural elements. The pyramid design demonstrates systems engineering understanding that integrates foundation, structural, and finish elements into coherent mathematical framework. Temporal engineering management required project coordination capabilities that maintain construction precision across decades of building activity. The consistency of mathematical relationships throughout pyramid construction suggests engineering management that can sustain quality control across extended construction periods involving thousands of workers. Workforce organization and training required engineering management that can transmit construction standards and quality requirements across large, complex construction teams. The precision achieved in pyramid construction suggests training and quality control systems that maintain engineering standards across diverse construction activities. Tool design and manufacturing required engineering capabilities that can produce cutting, lifting, and measurement instruments with precision necessary for mathematical constant encoding. The engineering precision evident in pyramid construction suggests advanced tool-making capabilities that exceed conventional estimates of ancient manufacturing technologies. Quality assurance systems required engineering methodology that can verify construction accuracy and detect deviations from target mathematical relationships. The mathematical precision achieved throughout pyramid construction suggests systematic quality control that can monitor and correct construction errors in real time. Construction sequencing required engineering planning that coordinates multiple construction activities while maintaining overall structural accuracy necessary for mathematical encoding. The complexity of pyramid construction demonstrates engineering management that can optimize construction sequences for precision and efficiency simultaneously. Materials engineering required understanding of stone properties, structural behavior, and long-term stability that enables precise construction using available materials. The engineering solutions evident in pyramid construction demonstrate advanced understanding of materials science and structural engineering principles. Structural analysis capabilities required engineering knowledge that can predict structural behavior and ensure stability while achieving mathematical precision. The pyramid design demonstrates understanding of structural engineering principles that optimize stability and accuracy simultaneously. Environmental engineering required understanding of climate effects, thermal expansion, and long-term environmental impacts on construction precision. The mathematical relationships preserved in pyramid architecture across 4,500 years suggest engineering design that accounts for environmental factors affecting structural accuracy. Risk management engineering required capabilities that can identify and mitigate construction risks that threaten mathematical precision targets. The successful achievement of mathematical encoding suggests engineering management that can anticipate and address potential construction problems that could compromise accuracy targets. Innovation and adaptation engineering required capabilities that can develop new solutions for unprecedented construction challenges. The unique requirements for mathematical constant encoding likely required engineering innovations that exceed standard construction practices available in ancient Egypt. Systems integration engineering required capabilities that coordinate multiple engineering disciplines while maintaining overall project accuracy. The pyramid construction demonstrates systems engineering that integrates structural, mechanical, and precision measurement systems into coherent construction methodology. Documentation and communication engineering required methods for preserving and transmitting construction standards across complex construction projects. The consistency of mathematical relationships suggests engineering documentation that can maintain construction accuracy across large, distributed construction teams. Testing and verification engineering required methods for confirming construction accuracy and validating mathematical relationships during construction. The mathematical precision achieved suggests engineering methodology that includes systematic testing and verification protocols. Research and development engineering required capabilities for investigating and developing construction methods necessary for achieving unprecedented precision targets. The unique requirements for mathematical encoding likely required engineering research that extends beyond conventional ancient construction practices. Maintenance and preservation engineering required understanding of long-term structural behavior and preservation requirements. The survival of mathematical relationships across millennia suggests engineering design that anticipates and addresses long-term preservation challenges. Technology transfer engineering required capabilities for implementing advanced construction techniques across large construction projects. The widespread application of precision construction throughout pyramid architecture suggests engineering methodology that can transfer advanced techniques effectively. Standards and calibration engineering required methods for maintaining measurement accuracy and construction standards across extended construction periods. The mathematical precision suggests engineering methodology that includes systematic standards maintenance and calibration protocols. The engineering capabilities demonstrated in pyramid construction thus encompass advanced understanding of surveying, structural engineering, materials science, project management, and quality control that could theoretically support intentional mathematical constant encoding. These capabilities challenge conventional assessments of ancient technological sophistication while providing context for evaluating claims about intentional mathematical encoding in pyramid architecture. Archaeological evidence. Archaeological discoveries surrounding the Great Pyramid and ancient Egyptian civilization provide crucial evidence for evaluating whether the mathematical sophistication required for constant encoding represents feasible ancient achievement or modern misinterpretation. Physical artifacts, construction evidence, and technological remains offer objective data for assessing ancient capabilities while revealing the broader context of Egyptian mathematical and engineering knowledge. The Rhine Papyrus, dating to approximately 1650 BC, documents Egyptian mathematical capabilities that include sophisticated geometric calculations, algebraic problem solving, and numerical techniques that demonstrate advanced mathematical understanding centuries before them. Conventional dates assigned to mathematical development in other cultures. This mathematical papyrus provides direct evidence for computational capabilities that could support complex architectural mathematics. The Moscow Papyrus, dating to approximately 1850 BC, contains mathematical problems that demonstrate understanding of three-dimensional geometry, volume calculations, and complex geometric relationships. The papyrus includes problems involving truncated pyramids that require mathematical understanding directly applicable to pyramid construction and geometric analysis. Ancient Egyptian mathematical tools and instruments recovered through archaeological excavation demonstrate precision measurement capabilities that could support the accuracy required for mathematical constant encoding, surveying equipment, measuring rods, and calculation aids reveal technological sophistication that exceeds conventional estimates of ancient measurement capabilities. The Turing King list and other chronological documents provide historical context for Egyptian technological development that supports the possibility of advanced mathematical knowledge. During pyramid construction periods, these historical records document continuity of technological and intellectual achievement across Egyptian dynasties that could support cumulative mathematical development. Hieroglyphic mathematical notation systems demonstrate sophisticated symbolic representation that enables complex mathematical communication and calculation. The Egyptian numerical and geometric notation systems provide the intellectual infrastructure necessary for developing and transmitting the advanced mathematical knowledge required for constant encoding. Construction artifact analysis reveals evidence for advanced engineering capabilities that support claims of mathematical precision in pyramid construction. Stone cutting tools, lifting equipment, and construction aids demonstrate technological sophistication that enables the precision construction necessary for mathematical encoding. The Palermo stone and other astronomical records document Egyptian understanding of celestial mechanics that could provide observational foundations for determining fundamental physical constants. These astronomical inscriptions reveal systematic observation programs that could theoretically support investigation of electromagnetic phenomena. Comparative analysis of other Egyptian monuments reveals consistent application of advanced mathematical principles across multiple construction projects, suggesting systematic knowledge rather than isolated achievement. The mathematical relationships found in pyramid architecture appear throughout Egyptian monumental construction, indicating widespread application of advanced mathematical principles. The Abydos helicopter hieroglyphs and other controversial inscriptions suggest possible preservation of advanced technological knowledge within Egyptian symbolic systems. While interpretation remains debated, these symbols demonstrate preservation mechanisms that could theoretically maintain advanced knowledge within artistic and religious contexts. Ancient Egyptian metallurgical artifacts demonstrate technological capabilities that exceed conventional estimates of ancient materials science. Advanced alloys, precision metalworking, and sophisticated chemical techniques suggest technological sophistication that could support advanced engineering and mathematical applications. The Dendero zodiac and other astronomical artifacts demonstrate sophisticated understanding of celestial mechanics that requires advanced mathematical calculation capabilities. These astronomical representations reveal mathematical understanding that could theoretically support investigation of fundamental physical constants through astronomical observation. Papyrus preservation and library systems demonstrate sophisticated knowledge preservation mechanisms that could maintain advanced mathematical and scientific understanding across historical periods. The systematic preservation of technical knowledge through Egyptian institutional systems provides mechanisms for maintaining mathematical sophistication across generations. Construction material analysis reveals engineering sophistication that supports claims of advanced construction capabilities. The precision achieved in material selection, preparation, and application demonstrates technological understanding that enables the accuracy required for mathematical constant encoding. The Serapeum of Saqqara contains massive granite boxes that demonstrate precision machining capabilities that exceed conventional estimates of ancient technological achievement. These artifacts reveal engineering and manufacturing capabilities that support claims of advanced ancient technological sophistication. Archaeological dating evidence provides chronological context for evaluating claims of advanced ancient mathematical knowledge. Radiometric dating, stratigraphic analysis, and historical correlation establish temporal frameworks for assessing the development and preservation of advanced mathematical capabilities. Cultural artifact analysis reveals intellectual context for advanced mathematical achievement through artistic, religious, and literary remains that demonstrate sophisticated mathematical understanding integrated within Egyptian cultural systems. These artifacts reveal the cultural infrastructure necessary for developing and maintaining advanced mathematical knowledge. Trade and communication evidence demonstrates international connections that could facilitate knowledge exchange and technological transfer supporting advanced mathematical development. Archaeological evidence for extensive ancient trade networks provides mechanisms for cultural and intellectual exchange that could support mathematical advancement. Educational system artifacts including scribal schools and training materials demonstrate institutional mechanisms for developing and transmitting mathematical knowledge. The systematic educational infrastructure evident in archaeological remains provides the institutional foundation necessary for mathematical advancement. Construction waste and tool mark analysis provides direct evidence for construction techniques and technological capabilities employed in pyramid construction. Physical evidence from construction processes enables objective evaluation of engineering capabilities and construction precision achieved by ancient builders. Site preparation and foundation evidence demonstrates engineering capabilities that support claims of precision construction necessary for mathematical encoding. Archaeological investigation of pyramid foundation systems reveals engineering sophistication that exceeds conventional estimates of ancient technological capabilities. Workshop and manufacturing site archaeology reveals technological capabilities for producing tools and equipment necessary for precision construction. Evidence from ancient manufacturing sites demonstrates technological sophistication that could support advanced engineering applications. Astronomical alignment evidence demonstrates precision in site orientation and architectural placement that requires advanced surveying and astronomical knowledge. The accuracy of astronomical alignments provides direct evidence for capabilities that could support mathematical constant determination and encoding. Preservation condition analysis reveals construction quality and engineering understanding that enables long-term structural stability while maintaining mathematical precision. The preservation state of pyramid architecture provides evidence for engineering capabilities that consider both immediate construction requirements and long-term preservation needs. Comparative architectural evidence from other ancient cultures reveals similar mathematical encoding in structures worldwide, suggesting widespread development of advanced mathematical knowledge in ancient times. Cross-cultural comparison provides context for evaluating Egyptian achievements within broader patterns of ancient mathematical development. Iconographic and symbolic evidence demonstrates preservation mechanisms that could maintain mathematical knowledge within artistic and religious systems. The integration of mathematical concepts within Egyptian symbolic systems provides pathways for preserving advanced knowledge across cultural and temporal boundaries. Technological sequence analysis through archaeological stratigraphy reveals the development timeline for Egyptian engineering and mathematical capabilities. The progression of technological achievement evident in archaeological remains provides chronological context for evaluating claims of advanced mathematical knowledge. Laboratory analysis of construction materials and techniques reveals engineering sophistication through microscopic examination of construction details. Scientific analysis of pyramid construction provides objective evidence for technological capabilities and construction precision that supports evaluation of mathematical encoding claims. The archaeological evidence thus provides substantial support for ancient Egyptian technological and mathematical capabilities that could theoretically enable the precision required for mathematical constant encoding, while revealing the broader cultural and institutional context that could support the development and preservation of advanced mathematical knowledge in ancient civilizations. Global patterns. Mathematical encoding appears in ancient structures worldwide, suggesting that sophisticated mathematical knowledge and constant preservation represent global phenomena rather than isolated Egyptian achievement. Cross-cultural analysis reveals consistent patterns of mathematical sophistication that challenge conventional narratives about the development and distribution of advanced mathematical understanding throughout ancient civilizations. Stonehenge demonstrates astronomical alignments that encode Earth's orbital mechanics with precision that requires advanced mathematical calculation and long-term observational capabilities. The monument's geometric relationships reflect sophisticated understanding of celestial cycles. including the 26,000-year precession cycle. That suggests mathematical knowledge comparable to Egyptian achievements in complexity and accuracy. The trilithon arrangements at Stonehenge embody geometric relationships that approximate fundamental mathematical constants, including pi and phi, through proportional relationships between stone positions and astronomical alignments. These mathematical encodings require construction precision that parallels the accuracy claimed for pyramid constant encoding. Angkor Wat incorporates cosmological constants into architectural proportions that demonstrate sophisticated mathematical understanding and precision construction capabilities. The temple complex embodies mathematical relationships that reflect Hindu cosmological time cycles, while encoding astronomical constants that require advanced mathematical calculation to determine and implement. The architectural proportions of Angkor Wat demonstrate understanding of advanced geometric principles, including the golden ratio, pi relationships, and complex trigonometric functions embedded within structural dimensions. These mathematical relationships require systematic mathematical knowledge and precision construction that parallels Egyptian pyramid achievements. Mayan pyramid architecture embodies mathematical relationships that encode astronomical constants and calendrical calculations with extraordinary precision. The pyramid of Kukulkan at Chichen Itza demonstrates shadow effects that track solar positions with mathematical precision that requires advanced understanding of geometric optics and astronomical mechanics. The Mayan long count calendar system demonstrates mathematical sophistication that includes understanding of large number systems, astronomical cycle calculations, and precise timekeeping that rivals modern chronometric accuracy. This mathematical achievement provides context for evaluating claims of advanced mathematical knowledge in ancient civilizations worldwide. The Antikythera mechanism represents direct archaeological evidence for ancient mechanical computing capabilities that could support the mathematical calculations required for fundamental constant determination. This device demonstrates technological sophistication that challenges conventional assessments of ancient computational capabilities. Across Mediterranean civilizations, Nazca lines demonstrate geometric precision across enormous scales that requires advanced surveying techniques and mathematical planning capabilities. The mathematical accuracy achieved in creating these ground figures suggests engineering and mathematical capabilities that parallel those required for pyramid constant encoding. Easter Island Moai positioning demonstrates astronomical alignments and mathematical relationships that require advanced calculation and construction capabilities. The systematic positioning of these monuments embodies mathematical principles that suggest widespread development of sophisticated mathematical knowledge across ancient cultures worldwide. The Göbekli Circle and other European megalithic structures demonstrate astronomical alignments and mathematical relationships that require advanced mathematical understanding and precision construction. These monuments reveal mathematical sophistication that extends across multiple ancient European cultures over extended time periods. Newgrange and other Irish megalithic monuments demonstrate mathematical relationships and astronomical alignments that require sophisticated geometric understanding and precise construction capabilities. The mathematical precision evident in these structures suggests advanced mathematical knowledge that parallels achievements attributed to other ancient civilizations. Chinese ancient mathematics demonstrates sophisticated numerical techniques and geometric understanding that could theoretically support mathematical constant determination and architectural encoding. Historical Chinese mathematical texts document computational capabilities that exceed conventional estimates of ancient mathematical development. The Forbidden City demonstrates architectural proportions that embody mathematical relationships reflecting Chinese cosmological principles and geometric constants. These mathematical relationships require systematic mathematical knowledge and precision construction that parallels achievements claimed for other ancient cultures. Indian temple architecture demonstrates systematic integration of mathematical constants and geometric principles within religious architecture across multiple historical periods. The mathematical sophistication evident in Indian architectural traditions provides additional context for evaluating ancient mathematical achievements worldwide. The mathematical sophistication evident in Indian Sulba Sutras demonstrates advanced geometric understanding that includes Pythagorean relationships, pi approximations, and complex geometric constructions centuries before these concepts appeared in other mathematical traditions. This ancient mathematical knowledge provides additional evidence for widespread ancient mathematical sophistication. Persian astronomical sites demonstrate precision alignments and mathematical relationships that require advanced mathematical understanding and observational capabilities. The mathematical achievements evident in Persian astronomical traditions contribute to the pattern of ancient mathematical sophistication documented worldwide. The mathematical relationships encoded in Petra demonstrate geometric understanding and construction precision that parallels achievements attributed to other ancient civilizations. The architectural mathematics evident in Nabatean construction suggests widespread development of advanced mathematical knowledge across ancient cultures. Maltese megalithic temples demonstrate astronomical alignments and mathematical relationships that require sophisticated geometric understanding and construction capabilities. These ancient structures contribute to the global pattern of mathematical encoding that challenges conventional assessments of ancient mathematical development. The mathematical precision evident in ancient Mesopotamian mathematics, including Babylonian astronomical calculations and geometric understanding, provides additional context for evaluating ancient mathematical achievements. Babylonian mathematical texts document computational sophistication that could theoretically support fundamental constant determination. African monolithic architecture demonstrates mathematical relationships and engineering precision that parallel achievements attributed to other ancient civilizations worldwide. The systematic mathematical principles evident in ancient African architecture contribute to the global pattern of ancient mathematical sophistication. Australian Aboriginal astronomical knowledge demonstrates sophisticated understanding of celestial mechanics that requires mathematical calculation capabilities and long-term observational programs. This ancient astronomical knowledge provides additional evidence for widespread development of advanced mathematical understanding. The systematic patterns of mathematical encoding across diverse ancient cultures suggest common underlying principles or knowledge sources that enabled similar mathematical achievements. Despite geographical and temporal separation, the consistency of mathematical sophistication across ancient civilizations challenges conventional models of independent cultural development. Cultural diffusion models that could explain similar mathematical achievements across ancient civilizations include trade networks, migration patterns, and knowledge transmission systems that could distribute advanced mathematical understanding across geographical boundaries. These transmission mechanisms provide potential explanations for global patterns of mathematical sophistication. Independent development models suggest that advanced mathematical understanding represents natural outcomes of human intellectual investigation that emerge predictably when adequate institutional and technological support exists. This interpretation suggests that mathematical sophistication represents inherent human capability rather than exceptional achievement. Preservation mechanism analysis reveals how different cultures developed systems for maintaining mathematical knowledge across historical periods, enabling survival of sophisticated mathematical understanding despite political and cultural changes. These preservation systems contribute to the global pattern of mathematical encoding in ancient architecture. Quality control systems evident across ancient cultures demonstrate widespread understanding of precision requirements and accuracy standards necessary for mathematical encoding. The consistency of precision standards suggests systematic development of engineering and mathematical capabilities across multiple ancient civilizations. Educational and institutional systems that could support advanced mathematical development appear across multiple ancient cultures, providing the infrastructure necessary for developing and maintaining mathematical sophistication. These institutional foundations contribute to understanding how advanced mathematical knowledge could develop independently across multiple ancient civilizations. The global patterns of mathematical encoding thus reveal widespread ancient mathematical sophistication that challenges conventional narratives about mathematical development, while providing context for evaluating specific claims about constant encoding in pyramid Architecture. These patterns suggest that advanced mathematical knowledge represents achievable, ancient accomplishment rather than impossible anachronism. Critics and controversies. Academic criticism of pyramid speed of light encoding claims centers on methodological concerns, statistical analysis, and historical plausibility. Arguments that challenge extraordinary claims with rigorous scholarly evaluation. Understanding these criticisms provides essential context for objectively assessing the evidence while maintaining scientific standards for evaluating unconventional archaeological interpretations. Statistical coincidence arguments represent the primary academic criticism, contending that mathematical relationships between pyramid dimensions and physical constants fall within probability ranges expected for random correlation. Critics calculate that given sufficient dimensional measurements and mathematical operations, coincidental approximations of physical constants become statistically inevitable rather than evidentially significant. Measurement precision disputes challenge claims about the accuracy of pyramid dimensional measurements, arguing that construction tolerances and measurement uncertainties exceed the precision necessary for meaningful constant encoding. Academic archaeologists contend that ancient construction variations eliminate the mathematical precision claimed for speed of light relationships. The cherry-picking criticism argues that pyramid encoding proponents selectively highlight correlations while ignoring failed relationships that contradict constant encoding theories. Critics demonstrate that mathematical operations applied to pyramid dimensions yield numerous correlations that don't correspond to physical constants, suggesting that reported successes represent selective interpretation rather than systematic encoding. Historical anachronism arguments contend that ancient Egyptians lacked the conceptual frameworks necessary for understanding fundamental physical constants like light speed. Critics argue that electromagnetic theory and light speed concepts require scientific understanding that didn't develop until modern physics, making ancient encoding historically implausible. Construction purpose arguments suggest that pyramid builders focused on practical construction requirements rather than mathematical constant encoding, making claimed relationships coincidental byproducts of engineering decisions rather than intentional mathematical preservation. Critics emphasize that pyramids served religious and burial purposes that don't require advanced mathematical encoding. Measurement unit controversies challenge claims about ancient Egyptian units and their relationships to modern measurement systems. Critics argue that uncertainty about historical measurement standards eliminates the precision necessary for meaningful comparison between ancient dimensions and modern physical constant values. Mathematical cherry-picking disputes focus on the arbitrary selection of scaling factors and mathematical operations used to derive physical constants from architectural dimensions. Critics demonstrate that sufficiently flexible mathematical manipulation can produce desired results regardless of underlying architectural intentions. Peer review criticism highlights the lack of publication in mainstream archaeological journals for pyramid encoding claims, suggesting that these theories don't meet academic standards for scholarly evidence and methodological rigor. The absence of peer-reviewed support indicates problems with evidence quality or interpretive methodology. Reproducibility concerns challenge claims that independent researchers can verify mathematical relationships between pyramid dimensions and physical constants. Critics argue that measurement uncertainties and interpretive flexibility prevent reliable reproduction of claimed mathematical correlations. Alternative explanation arguments propose conventional interpretations for observed mathematical relationships that don't require advanced ancient knowledge. Critics suggest that aesthetic proportions, construction convenience, and religious symbolism provide simpler explanations for architectural mathematics. Burden of proof disputes center on epistemological questions about what level of evidence justifies acceptance of extraordinary claims about ancient knowledge. Critics argue that exceptional claims require exceptional evidence that exceeds the standards applied to conventional archaeological interpretation. Historical precedent arguments contend that claimed ancient mathematical sophistication lacks support from documented historical development of mathematical knowledge. Critics emphasize that mathematical development typically requires cumulative institutional Development that isn't documented for ancient Egypt. Archaeological context criticism argues that pyramid encoding claims ignore broader archaeological evidence about ancient Egyptian culture, technology, and intellectual capabilities. Critics contend that encoding theories don't integrate with established archaeological understanding of Egyptian civilization. Scientific methodology disputes challenge the analytical approaches used to derive physical constants from architectural measurements. Critics argue that proper scientific methodology requires hypothesis testing, control studies, and statistical analysis that encoding proponents don't provide. Cultural projection concerns suggest that pyramid encoding theories reflect modern scientific concepts inappropriately projected onto ancient cultures. Critics argue that constant encoding represents contemporary physics misapplied to historical contexts that couldn't have possessed relevant scientific frameworks. Occam's razor applications favor simpler explanations that don't require extraordinary ancient knowledge claims. Critics argue that conventional interpretations provide adequate explanations for observed phenomena without invoking advanced ancient scientific capabilities that lack independent historical support. Professional consensus arguments emphasize that mainstream archaeology, Egyptology, and physics reject pyramid encoding claims due to methodological problems and insufficient evidence. The absence of professional acceptance suggests fundamental problems with encoding theories and supporting evidence. Educational impact concerns focus on how pyramid encoding theories might mislead public understanding about ancient history and scientific methodology. Critics worry that popularized encoding claims promote misunderstanding about historical development of scientific knowledge and appropriate standards for evaluating extraordinary claims. Pseudoscience classification disputes arise when critics categorize pyramid encoding theories as pseudoscientific due to methodological problems, resistance to falsification, and promotion outside peer-reviewed academic channels. This classification challenges the scientific credibility of encoding claims. Response to criticism from encoding proponents includes challenges to academic methodology, claims of institutional bias, and arguments that conventional archaeology underestimates ancient capabilities. Proponents argue that academic conservatism prevents recognition of extraordinary ancient achievements. Methodological counterarguments from proponents include precision measurement data, statistical analysis supporting correlation significance, and systematic documentation of mathematical relationships across multiple architectural features. These responses attempt to address academic concerns about evidence quality and statistical methodology. Historical counterarguments from proponents include evidence for advanced ancient mathematics, technological capabilities exceeding conventional estimates, and cross-cultural patterns suggesting widespread ancient mathematical sophistication. These arguments challenge critics' assumptions about historical limitations. Evidence standards disputes reflect fundamental disagreements about appropriate criteria for evaluating extraordinary claims about ancient knowledge. Proponents argue that critics apply unreasonably high evidence standards that wouldn't be applied to conventional archaeological interpretations. Institutional bias claims from proponents suggest that academic institutions resist pyramid encoding theories due to ideological commitments to conventional historical narratives, rather than objective evidence evaluation. These claims challenge the neutrality of academic criticism. Future research directions include improved measurement techniques, expanded statistical analysis, and interdisciplinary collaboration that might resolve current disputes about pyramid encoding. Both critics and proponents acknowledge areas where additional research could strengthen evidence evaluation. Publication strategy disputes reflect disagreements about appropriate venues for presenting encoding research, with critics demanding peer review and proponents arguing that institutional bias prevents fair academic evaluation. Popular support for pyramid encoding theories creates tension between academic skepticism and public interest in alternative archaeological interpretations. This dynamic affects how encoding theories develop and gain acceptance outside academic institutions. Educational responsibility questions arise regarding how educators should present controversial archaeological claims while maintaining scientific standards and public understanding of appropriate evidence evaluation methods. The ongoing controversy thus reflects fundamental tensions between extraordinary claims and academic standards, conventional interpretation and alternative theories, and popular interest versus professional consensus, requiring careful evaluation of evidence, methodology, and appropriate standards for assessing claims about ancient knowledge and capabilities. Scientific testing. Rigorous scientific evaluation of pyramid speed of light encoding claims requires systematic measurement, statistical analysis, and experimental validation using contemporary precision instruments and mathematical techniques. Modern scientific methodology enables objective assessment of mathematical relationships while establishing evidence standards appropriate for evaluating extraordinary claims about ancient knowledge. Encoding. Laser measurement technology provides unprecedented precision for determining pyramid dimensions with accuracies that exceed ancient construction tolerances by orders of magnitude. High-precision laser scanning can detect dimensional variations measured in millimeters across structures spanning hundreds of meters, enabling accurate evaluation of mathematical relationships claimed for constant encoding. The Global Positioning System enables precise georeferencing of pyramid measurements within coordinate systems that support accurate mathematical analysis. GPS technology allows researchers to establish measurement frameworks with positional accuracy sufficient for detecting the geometric relationships claimed for mathematical constant encoding. Photogrammetry techniques using high-resolution digital imaging enable detailed measurement and analysis of pyramid features with precision that supports systematic evaluation of mathematical relationships. Digital measurement techniques can process thousands of measurement points to establish dimensional datasets appropriate for statistical analysis of encoding claims. Ground-penetrating radar and other subsurface scanning technologies reveal internal structural features that provide additional data for evaluating mathematical relationships. Throughout pyramid architecture, these technologies enable comprehensive analysis of architectural mathematics beyond external dimensional measurements. Statistical significance testing using contemporary mathematical techniques can objectively evaluate whether observed mathematical relationships exceed probability thresholds for random correlation. Modern statistical methods enable rigorous assessment of claimed mathematical correlations while controlling for multiple comparison problems and data mining effects. Monte Carlo simulation techniques can generate probability distributions for mathematical correlations between architectural dimensions and physical constants, providing objective standards for evaluating the significance of observed relationships. These computational methods enable quantitative assessment of correlation probability. Measurement and certainty analysis using error propagation techniques enables realistic assessment of precision limitations in architectural measurements and their effects on claimed mathematical relationships. Understanding measurement uncertainties provides essential context for evaluating the significance of mathematical correlations. Blind measurement protocols can eliminate researcher bias in dimensional measurement by employing measurement teams without knowledge of specific mathematical relationships being tested. These methodological controls ensure objective data collection that supports unbiased evaluation of mathematical correlation claims. Independent replication studies enable verification of measurement results and mathematical correlations by research teams using different equipment and methodological approaches. Successful replication provides essential validation for scientific claims, while failed replication identifies methodological problems or spurious correlations. Control studies using randomly selected architectural features can establish baseline probability levels for mathematical correlations in ancient architecture generally. These control measurements provide comparative context for evaluating whether pyramid mathematical relationships represent systematic encoding or typical architectural mathematics. Cross-validation techniques using different mathematical approaches and scaling factors can test the robustness of claimed mathematical relationships while identifying analysis methods that might generate spurious correlations. Mathematical validation ensures that observed correlations represent genuine architectural features rather than analytical artifacts. Computational analysis using automated pattern recognition can systematically search architectural measurement databases for mathematical relationships. providing comprehensive evaluation of encoding claims while identifying additional correlations that might support or refute encoding theories. Experimental archaeology techniques can investigate whether claimed mathematical precision could be achieved using construction methods available in ancient Egypt. Reconstruction experiments using traditional tools and techniques can evaluate the practical feasibility of mathematical encoding within ancient technological constraints. Metrological analysis using historical measurement systems can evaluate whether ancient Egyptian units could support the precision required for mathematical constant encoding. Understanding ancient measurement capabilities provides essential context for evaluating encoding. Feasibility. Construction simulation using computer modeling can test whether mathematical constant encoding represents feasible construction objectives or would require impossible precision given ancient technological limitations. These simulations provide quantitative assessment of encoding. Plausibility. Materials analysis of pyramid construction elements can reveal precision limits achievable using ancient construction techniques and materials. Understanding material properties and construction tolerances provides context for evaluating claims about mathematical precision in ancient architecture. Historical validation through documentary analysis of ancient mathematical texts can establish whether Egyptian mathematical knowledge could theoretically support constant encoding activities. This research provides historical context for evaluating encoding plausibility within documented ancient capabilities. Comparative analysis of mathematical relationships in other ancient structures can establish whether pyramid mathematical patterns represent unique encoding or typical ancient architectural mathematics. Cross-structural comparison provides broader context for evaluating pyramid mathematical claims. Temporal analysis of measurement data can distinguish between original construction mathematics and later modifications or measurement errors that might affect mathematical correlation analysis. Understanding measurement chronology ensures analysis focuses on genuine ancient architectural features. Quality assurance protocols using multiple measurement techniques and analysis methods can identify systematic errors or methodological problems that might affect mathematical correlation results. These protocols ensure reliable data collection and analysis for scientific evaluation. Peer review processes involving mathematicians, physicists, and archaeologists can provide interdisciplinary evaluation of encoding claims and supporting evidence. Professional review ensures that claims meet appropriate scientific standards across relevant academic disciplines. Publication standards requiring detailed methodology documentation and raw data availability enable independent verification of research results and analysis methods. Transparent research practices support scientific validation of extraordinary claims about ancient knowledge. Falsifiability testing can establish specific criteria that would refute encoding claims, providing clear standards for objective evaluation. Scientific theories require testable predictions that enable objective validation or refutation. Based on empirical evidence, meta-analysis of multiple independent studies can provide comprehensive evaluation of encoding evidence while identifying consistent patterns or systematic problems across different research approaches. Systematic review enables objective assessment of cumulative evidence quality. Technology validation ensures that measurement instruments and analysis techniques provide appropriate precision and accuracy for evaluating mathematical encoding claims. Understanding technological limitations prevents overinterpretation of measurement results. Educational standards for presenting research results ensure that scientific findings are communicated accurately without oversimplification or misrepresentation that might mislead public understanding. Responsible science communication maintains appropriate uncertainty acknowledgement and evidence qualification. Funding transparency for research projects enables evaluation of potential bias sources while ensuring that research independence supports objective scientific evaluation. Understanding research funding sources provides context for assessing potential influence on research conclusions. Collaboration protocols between encoding proponents and critics can establish mutually acceptable research standards and evaluation criteria that enable objective assessment of controversial claims. Scientific collaboration can bridge methodological disputes while maintaining rigorous evidence standards. Data archiving requirements ensure that measurement data and analysis results remain available for future verification and reanalysis using improved techniques. Long-term data preservation supports continuing scientific evaluation as analytical methods advance. The application of rigorous scientific testing methodology thus provides objective standards for evaluating pyramid encoding claims while distinguishing between genuine mathematical relationships and coincidental correlations. These scientific approaches enable evidence-based assessment of extraordinary claims while maintaining appropriate skepticism and methodological rigor. Modern implications. The potential validation of ancient mathematical constant encoding in pyramid architecture carries profound implications for understanding human intellectual development, technological capabilities, and knowledge preservation mechanisms that extend far beyond archaeological curiosity to influence contemporary science, education, and cultural understanding worldwide. Educational transformation represents one of the most immediate implications, as recognition of advanced ancient mathematical knowledge requires fundamental revision of curricula in history, mathematics, and science. Educational institutions worldwide would need to integrate understanding of ancient mathematical achievements while developing new pedagogical approaches that acknowledge the sophistication of historical human intellectual accomplishment. The decolonization of mathematical and scientific history gains momentum through recognition that advanced mathematical knowledge developed independently across multiple ancient cultures. Rather than progressing linearly through conventional historical narratives, this broader perspective reveals mathematics and science as truly global human achievements that transcended cultural boundaries throughout history. Archaeological research methodology undergoes transformation as recognition of advanced ancient capabilities demands new analytical approaches that consider technological and intellectual sophistication previously deemed impossible. Archaeological investigation requires expanded analytical frameworks that can identify and interpret advanced ancient knowledge. Preservation mechanisms.